Okay everyone, sorry for late. Some technical disturbance occurs here, that's why I am late. Now let's start the session. I have taken up question number first. A non-inverting buck boost converter shown in the figure is driven by a current hysteresis current using a hysteresis band delta H. Hysteresis band same as the delta IL of inductor current. And what will be the expression of its steady state switching frequency? Therefore, the option is given here. We are asking about the switching frequency. This is given on time, this is off time. This is a buck converter, buck boost converter. The switching is given like this one. Q is 1, it means the switch is on. This one and this one is on. Even if Q is equal to 0, then this switch and this switch will be on. S bar. Take a first one like switch Q is equal to 1 and switch S is only on. When switch S is on and current flow like that, V into VL. And what will be the VL in this condition? You know about VL, same as the V in. It works like a same as a buck boost converter, but polarity of output is the positive term. In conventional buck boost converter, the polarity of output voltage is a negative. Okay. We know about the volt second balance equation, same applied. When switch is on, VL is equal to V in, and switch is off, it means Q is equal to 0, then this switch will be on, and VL is a figures on the output voltage, like this plus 1 connected to the minus 1 and like that, and negative 1 connected to the positive of output voltage. That's why in this condition VL is equal to minus of V naught. Now you know about the volt secondary valence equation of buck boost converter. Okay. So now so okay. Yes. Wait. I disconnect and connect once again. Actually here electricity has gone suddenly, that's why I faces some problem. Now switch is on, the inductor voltage appears V in supply voltage, and when switch is off, then inductor voltage appears as the output voltage. Then yes. Yes, yes. No. So in this one, don't think like that. When switch is on, then both are switches is closed. When switch is off, then this switch is closed. That's why it is when switch is on, then dt times, and switch is off, then 1 minus dt times off with this one. Total time period is dt plus 1 minus dt. Total time period is t only. Like that, when the conventional boost converter, then one switches and one diode is there. But here diode replaced by the switches. And another switches is used to convert the output as a negative output to the positive output. Then these switches will directly give a supply, give a pulse like a dt times a duty pulse. When switch is on, then two switches are on at the same time. That's why this is the on time and this one is the off time. Total time period is this one on time plus off time only. Same thing apply a volt second valence equation, and IL this one M1 and this one M2, IL current for this one. Then what will be the M1 slope? Slope will be the voltage. This was, if you know about this, L di by DIL by dt is equal to V in. Then DIL by dt is this one the slope of inductor current. It's like that. When switch is on time, slope is M1. The M1 is V in divided by L. This is the slope of on time inductor current. V in divided by L. Same thing if you focus here, VL is L di by dt minus of V naught. Then slope is DIL by dt is the slope of anything, dy by dx is the slope. And then minus of V naught by L. This one is denoted as a minus of M2. Then M2 is V naught by L and M1 is V in by L. This one is denoted as an inductor current. This one switch is on, this one switch is off. The average voltage of inductor is 0. This is a volt second valence equation. And what is the slope? Voltage of, if the slope is given, the voltage is M1 into L. Same thing happened, or I am written directly as V in voltage. V in into T on voltage plus V in into, when switch is off, the minus of V naught appears here. V naught into T off divided by total time period is equal to 0. This is the average voltage of inductor. Average voltage of inductor will be 0 by the volt second valence equation. Then what is the V naught? V naught, if you find there, T naught goes to that side 0, and V output is V in into T on divided by T off. You know, in a conventional buck boost converter, T on is equal to d dt, and T off is equal to 1 minus dt. Then same is written as V output is equal to V in into dt divided by 1 minus d into t. T cancel out, V in d divided by 1 minus d. This is the conventional buck boost converter output voltage equation. Same thing written as a T on and T off in this questions. Once you find a output equation, then find the delta IL. Delta IL is the same as the delta H. Delta IH is equivalent. Then what will be delta IL or delta IH? This one the minimum current, this one the maximum current. Same apply when switch is on. VL is equal to V in L di by dt is equal to V in, then DIL is equal to V in divided by L into dt. Inductor current integration from I minimum to I maximum, minimum to IL maximum, and the time taken by the 0 to T on time, like that. Here if you integrate this one, you find IL maximum minus IL minimum is same as delta IH is equal to V in divided by L into T on. You find the two equation, V output and delta IL. So now written here. In this equation, you can written as a V output divided by V in is equal to T on divided by T off. If you add this one plus 1 to let both sides, then you find V output plus V in divided by V in and T on plus T off divided by T off. This will be T divided by T off. Works. It as a V output plus V in divided by T is equal to V in divided by of T off. Then V in divided by T off is equal to here, from here you can written as V output divided by T on. Okay. V output is equal to V out, V in divided by of T into T on. From here you can replace T on delta IH into L divided by of V in, replace here, then you find V output is equal to V output plus V in into divided by a time period in T on, replace by here delta IH into L V in 1 by T, you can write as a frequency then F is equal to V in into V in, V output into V in divided of V output plus V in into 1 by delta IH into L. This is the switching frequency of this converter. First of all, find V output voltage, then match this one, V output into V in divided by V output plus V in into 1 by delta IH. Switching frequency, I think this one, first one, V output into V in divided by V in plus V output into 1 by L into delta IH. Okay. Find the output voltage, after that find the ripple of this one. Okay, good. Want something? Yes? This one. Simply write 1 plus 1 here. Then we find the V output plus V in divided by V in. Here. Here. Then this one is the V output plus V in. Then V in can transfer here and T transfer here. Then V output plus V in here. Okay, replace this one. V output plus V in divided by T. Now this one is V in by T of. Can do this. V in by T of minus V in by. No, I simply replace this one. V output plus V in. Okay, this one V in is equal to T divided by of T of. I simply replace, transfer this one. Replace the V in by T and V in goes to there. V output plus V in divided by of T is equal to V in divided by of T of. And this one can replace from here. To find T on and T on replace from delta IH. Okay. Next question of push-pull converters in the figure supply a 30 ampere constant load at V output at 24 volt. The turn ratio of the transformer is 2 primary to secondary. It means this one is 2, this one is 1 transfer ratio. The on-state voltage drop of diodes and transistors is 0.5 and 1 volt. 0.5 volt for the diode, turn on voltage drop, and 1 volt is a transistor. This one. So actually this was the IGBT, transistor. What is the average input current is asking. The transformer has 0 losses in leakage. It means resistance of the primary winding, secondary winding is 0. Leakage means inductance also 0. The load current in input current have a negligible ripple. That's why so is constant output voltage and output current. This one here. The push-pull converter is looks like a 2 winding, supply voltage given here, and switches. There are 2 switches. This one is a positive voltage and this one negative voltage supply. So light a Q1 and Q2. It is on transformer a inductor and a capacitor, same as the buck converter, because a push-pull converter also is a buck converter, but it's an isolated buck converter. Capacitor, inductor, output voltage. So now I put current. Okay, diode D1, D2. Primary side at turn ratio, and this one is secondary side turn ratio. Dot convention is like that for push-pull converter. The nano basic push-pull converter, it looks like that. This one is given as a constant output current and constant voltage. That's why it taken a constant output and constant voltage. I replace this thing by a constant current and constant voltage. But if not constant voltage and current, that's why it looks this one. VL. We take this as a VP. This one also VP. Primary voltage. So secondary voltage, like that. In push-pull converter, first one switch 1 is on and operation is doing. After that, switch on is closed. Switch on means both are switches not closed. This switches are off. Now, and that time inductor current is release the energy. Inductor release the energy that time. After that is switch off Q2 on. It is process like a double process here. When switch is on, then another same process occurs and requires charge and discharge. After that switch 2 is on, then same process occurs. Switch inductor is charge and discharge. First I take as Q1 is on. Then what will happen? And switch is, this one is on, this one is off. It means current not flow here, current flow like that. VP is same as V in. Dot occurs here, V in. IC current is 9 on D1 D2. Dot convention is here. This is the primary winding current, secondary winding. Dot convention shows that this one is if this one is a positive connected to this one positive terminal, then secondary side also this one positive, this one negative. This one positive, this one negative. This positive connected to the diode anode, that's why this diode will be forward wires. This negative connected to the anode of the second diode, and this one is the reverse wire, that's why the current will not flow here. And switch 1 is on, then current flow like that. After the switch is off, it means the both switches off. Q1 and Q2 already off, and Q1 is off, then this one is off condition like that. So not connected, current not flow here, I is equal to 0, and that time this secondary side winding we have like a impedance only. Then both our impedances will be same. That's why the current, remaining current of means discharging current of inductance output inductor is go to both sides, D1 and D2, through the D1 and D2. Not only a D1, because of the voltage is 0 here in input side. That means this is behave like an impedance only. but because of the same impedance of both winding is the same and both turn is the same, that's why current flow like that. Both are diode is on and discharge through it. And second time, if same process occurs when Q2 is on, Q2 is on, then that means this one is on here, this one positive, this one is positive. Sorry, this one is positive, negative, basically. That's why. One second. So current flow like that, then this one is positive, this one negative. It means dot convention is negative, on dot will be positive. On dot will be this one connected to the positive voltage, and this forward bias, and this will be in reverse bias. Because dot is negative. That's why this one reverse bias, current flow like that. And switch Q2 is on. And same thing when Q1 and Q2 both are off, it means Q2 off. Then the remaining current, remaining charge of because of charge of the inductor release the energy through both diode. Then you can take a waveform of this one. You can understand from the waveform. This one and Q1 is on, then this one is both off, Q2 on, both off. Notice the inductor current IL. When Q1 is on, this one, to Q1 current flow like that through the D1, or you can see this one is secondary 1, this one secondary 2. IS1 is flow like that. Then current will be, the inductor will be charged, and both are off, current will be discharged like that. And then Q2 is on, this one is charged, though both are off, discharged. And the IS1, secondary current of primary, first winding, second winding. And Q1 is on, the primary secondary current is flow like that. This one current, here, so look here, like that. This current, it means same inductor current flow through the primary one, although the first winding of the secondary. After when switch is off, then the inductor current flow to the both diode, both winding. That's why is a half of current flow from here and half of current flow from the secondary side. Same phenomenon occurs in IS2 when switch Q2 on. Then this current is flow from here IL, because of the IL and switch is on, all of current of inductor current flow through the secondary winding of secondary side, second winding of secondary side. After this one will remain 0. So both the switches off, then half of current flow from the here and half of current flow from here. Then what is the primary winding current? You can say that I in primary side current flow like NS by NP divided by of IS1. plus IS2. This is current. Input current flow when this Q1 is on, then this current flow through the primary winding. This current same as the NS, and if you transfer this one IL here in the primary side, then you can retain as NS divided by of NP into IL or IS1. This one current is IS1, same as IS1. In this condition, IS2 is 0, then same current flow, IS1 is here, and both are switches closed, open. If both the switches open like that, at that time the IN will be 0 because of no current flow in the primary winding, primary side. The whole of current flow through this one and this one, but in the primary side current will be 0. This condition is primary current will be 0. After same phenomenon occurs when the switch Q2 on, inductor current. This one look like that. After that, this one will be 0. Yes. 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 This one will be from when the switch is on, then this current will be 0. And this current will be 0, it means the same current flow through the secondary winding, and voltage will be 0 at that time. Should be 0, voltage should be 0 in that time. If you observe here, because of the input side voltage will be 0. Yes, then if input current is 0, then input voltage also 0 na, primary side. At primary side voltage also 0 at that time na. If current will not flow, then voltage will be 0. If you balance this one like plus minus, this one plus minus na, when switch, this one is on, when switch is off, both are off, then this current flow like that, and this will be positive and this will be negative because of this one act as a source sink at that time. If it will not act as a source, then polarity will be reverse. Then VS2 current should be flow like that, and VS1 is VS2 should be same because of the number of turns is equal. If number of turns is equal, then voltage should be 0 from here to here. That's because of primary voltage also 0, the secondary should be 0 voltage. That's why if this voltage, this one is the secondary voltage na, from here to here, if you measure this one, then this one also primary voltage. And this should be balanced now. By number of turns is same, then this one is VS1 is the same as the VS1. Here also number of turns is same and current will flow same through the secondary winding, both secondary winding. Then you can apply a keep here like that, minus V plus VS1. Minus plus VS will cancel out, then whole of voltage will be 0. In that condition, that's why current flow through the both winding. to balance it, or you can also observe that this one number of turns is will same. I mean, if number of turns will same, then it will behave as a same impedance. If same impedance in both the side, then current will be flow through the both winding. If one turn number of turns is greater than the second one, then current will be also divided. Yes. Q2. Yes. Q2 is off, then Q1 is contact, and when Q1 is contact, Q2 will be off. Yeah. If Q1 is conducted, then D1 will be conduct and D2 will be off. And this current in primary winding like that, and secondary winding like that. And that time, because of the primary winding voltage is the same as V in voltage or BP voltage. This voltage appears both winding. Because of the number of term is same, then this one voltage appears, both voltage will be same. Then this Vs1, Vs2 is the same. Then Vs1 is positive applied to the primary D1. Then this one will be forward bias. Then Vs1 is occurs here. And same time Vs2 is same as Vs1, but in the negative terminal to apply here. That's why this one is positive, this one negative, this one will be reverse bias. Then D2 will be not conduct. But when both switches off, it means the primary voltage will be 0. Not any voltage appears on the primary winding. Then the secondary side should be voltages will be 0 for the both winding. That's why current flow through like that to both the winding in that condition. D1, D2 both. Yes. When Q2 off, then store charge on inductor, current flow like this one. The primary winding also and half of the secondary dart. Current flow through the both winding. If the same current flow, half of current flow the both winding, means both current will be same, primary side, secondary side are both winding, and number of turns will be same. That's why voltage is also same, the secondary side voltages. That's why the apply a KVL here, then voltage will be 0 from minus to plus. If current flow like that, this one will be positive, this one will be negative. But the current flow here like that, then this one is positive, this one will be negative. If you apply KVL, the secondary side voltage will be 0. Primary side voltage also 0 because of both are switches open. That's why secondary side should be balanced. Yeah. Yes, sir. Who can't take a different because of the inductor also. As output inductor, I have output inductor. Now, if you apply this one is in D1 time, like this one, if this voltage is more, if Q1 is on and number of turns is different, then this one will be more from this one. If this voltage will be more, it means current will be also more. If VL will be V in, so it will be NS divided by NP into VL. Hence Q1 is on, and when Q2 is on, VL will be NS divided by NP into Vs. This one, if you take Vs1, NS1, NS2. If this one is more and this one is less, then this pairs the more voltage, it means more current flow through the diode, through the inductor, and this time less current flow through the inductor. Then this will be some differences occurs here, off time, and this one is on time. Then inductor goes to saturation because of the unbalance of the fluxes in primary to secondary, and it should be same when both phenomena. When both phenomena occurs, will be same. Current will be same. A voltage which appears on the inductor should be same in both conditions. That's why a number of turns will be should be equal. Yes, yes, sir. BP is same as the VS, na? This one, B in. This one is occurs. Oh, sorry, VL, this one minus V now, P naught. Sorry. And switch is on, you appear this one voltage plus minus of this one voltage in VL. Now it's okay. Yeah. I have taken because the VP is same as the V in, yeah, VS. That's why. Yes. Okay, then VP will be VP. VP is the same as the V in, na? When this one switch is on, then this one same appears as the V in. That's why I take it as a VS. You can retain the VP. Okay, this one is a VP, but because of this one, if the switch is on, then the same appears as the primary winding. VP is same as the V in. Your polarity will be adjusted same like that. The polarity will be taken as reference. That's time a different voltage appears in the primary winding. Same thing in the question is given like that input and output voltage will be constant and all time. The given the constant load current 30 ampere and constant voltage. If a voltage or current is given as a constant, then you can say then this one is to take averages the current constant current flow I naught here, and switches both the switches off, then I naught by 2 flow here, same as I naught by 2 flow here. This one current is I naught by 2, half of current flow. If observe here and switch Q1 is on, this one switch on, this one primary current and secondary current flow like that. The whole of if given in the question as a constant current flow to doubt. Because if a constant current flow, it means whole of current flow through the secondary side. This I taken as the constant current as I naught. And the both switches is off, then half of current flow through the half up here and half up here. This one. First to find this voltage, new voltage. Take it like a Vx, and this one is the V naught, then what will be the VL voltage? VL will be Vx minus of V naught. And Vx is up here, isn't it? If this diode is off, this current flow through it, and this voltage will be this voltage, primary side, second is first voltage, Vs1, and Vs1 will be VA, Vs1 is the V in or Vp, you can say Vp into Ns divided by Np. This voltage. And what will be VL? If you apply a KVL like that, from here to here, then you find VL is will be Vx, Vx is will be Vs1, this voltage, minus of V naught. Sorry, this one Vx, VL is equal to Vs1 minus of V naught. And switch is off and switch is on. And switch is off, then inductor current is, this one will be 0 for voltage, because of the both voltage will be 0, same current flow through it. Then whole of voltage is 0 from here to here. To taken, then this one current is same up here as the V naught output voltage, and VL is be minus of V naught. On base both the switches is off. Then switch is on, then dt is apply here, and on minus dt is apply here. That's why the inductor current will be part of time Vx minus of V naught divided by L into T expression, or you can say that T on, and this time up minus of V naught by L. Yes. Same as the buck converter, no? Looks like this one is the buck converter. Yeah, then you can say like if VL is I will written as a Vx minus of V naught, then L di by dt is equal to Vx minus of V naught, then DIL is equal to Vx minus V naught divided by L into dt. Integrate both one with this one. If you integrate, then IL, this one is Vx minus of V naught divided by L into time t plus some constant. If you integrate this one, you find some constant. K is same as the I male minimum at that time. Same if you appears in second side, both switches is off, then you find this one is like a L into T minus of TO plus K, and K1, this one is K1, this one is K2. K2 is the I L maximum, and IL maximum, IL max minus of IL minimum, you can take as a delta IL, and delta IL will be Vx minus of V naught divided by L into dt. Then I minimum, in this inductor IL is the same as a I output, then IL minimum you can retain as the delta I naught minus of delta IL divided by f2, and I maximum is the I naught plus delta IL divided by 2, like that. Looks here, if you take as a average as of inductor current, this one take as a this one IL, then this one IC, average of capacitor current will be 0 from the flux balance, charge balance, current second balance equation. Then the IL is average of the inductor current, same as the average of output current. And delta IL you can calculate it from here. Vx, when switch is on, then Vx minus V naught up here, VL is equal to Vx of minus of V naught, then VL same apply a VL by dt, Vx minus of V naught, and if you integrate this one delta IL to IL minimum to IL maximum, then you find delta IL. I written as here delta IL divided by delta T is equal to Vx minus of V naught. If you take delta IL, then Vx minus of V naught divided by FL. If you have integrate this one I minimum to I maximum, then so dt, time is respect to 0 to dt when switch is on time. At that time current flow from minimum to maximum slope will be occurs when switch is on. This one is on time. In this case, this one is I minimum, this one I maximum. If you integrate this one I minimum to I maximum, you find delta IL. Delta IL is Vx minus of V naught divided by L into Tt. You can find from here delta IL and IL maximum, IL minimum find from here. Then find the equation of this one. It's a directly depending on the time. If your time increases like that, there is slope of the inductor current will be linearly increases. Same thing with the T on because of this one. When switch is off, this one is a T on. That's why I have T minus T on taken in second side. When switch is off, then the slope will be linearly because of the time. Yes, direct apply to there. That's okay. The same expression same occurs in the buck converter, because of the whole of this one is a buck converter from here to here. That's why you can find there. I already explained in buck converter how to find the inductor current expression. But in the question is given, comes to the point on the questions. Then given a constant current flow and constant voltage, output voltage given. Then NP, NS, NP is given. I think this one is given like that. Vp, Vs, D1, D2. It will given a constant not current flow like given a 30 ampere. Output voltage is given 24 volt. Then what will be power? I output into V output. 720 watt. Then what will be the output voltage? This voltage. Again constant voltage, then constant voltage taken as the Vs minus of Vd. Can written like that. Vs minus of Vd. Voltage drop across the diode. This voltage drop Vs, this voltage minus of this voltage is equal to V naught. And switch is on this one. At that time, this V naught is equal to Vs minus of V naught, because of the inductor can not there. Sorry, not here. Inductor is given as the constant current is flow. That's why Vs is what is Vs? Vs is simply written as Vs is Vp into Ns divided by NP. This one voltage Vp into Ns divided by Np is equal to Vs minus of Vt. If you take a Vt1, then you can take Vd1, Vd2 is given as the same as 0.5 volt. Then what is the Vp? Vp is given as a voltage drop occurs across the switches also is given in the question. Is a 1 volt. On state voltage drop across the diode and transistor. Diode will be 5.5 volt, transistor will be 1 volt. That's why Vp is not same as V in this question. You can write a V in minus of 1 volt is equal to Vp into Ns divided by Np minus of Vd. The output voltage. And output voltage is given like a 24 volt. V in is not given. Minus 1 Ns divided by Np. Np divided by Ns is given 2. Then what will be Ns divided by Np is equal to 0.5. Then take a 0.5 here, and diode voltage is 0.5, drop voltage is given. Then what is V in? V in is equal to 24 plus 0.5 divided by 0.5 plus of 1 is equal to 50 volt. You find a V in, input voltage 50 volt. Okay, then what will the power of input power? Where is given? In this question, yeah, if the variation is V in, then you can't take directly like a V in. V in when the V in occurs 50 volt, when the V in is a constant only. If a V in variation, then you can't say directly V in is 50 volt. It's depending on the duty ratio. Duty ratio is not given here. That, yeah, if here duty ratio is not given, then you take a duty ratio is the same for all. If variation occurs in primary voltage or input side voltage, then duty ratio will be changed to maintain the constant output voltage. But here if not given, then take as the duty ratio will be same or constant. Then what will the power? P out input power, output power plus of power drop here, power, and this one switches power loss. We include this power loss. Transformer resistance is given as a 0, negligible here, 0 losses. That's why you can take a power loss of a transformer. Then output power plus of switches power. Switches voltage is given 1 volt into switches current ISW. 2 switches is given here. That's why you take as a average of this one is 2 switches, 1 into ISOW. Take ISW is average current. Then 0.5 is diode, 2 diode here. Power loss of this one, 2 diode. Output power plus all of losses. Output voltage plus we can take as a 2 ISW plus ID current, diode current. Switch is current, you can say this one is the switch current. If this one is given as a constant, then this will be constant current. Constant switch current flow here, primary side, switch 1 and switch 2. Then what will be one switch's current flow? You can say I in divided by up to total I in, divide half of I in is current flow, so half of the switches. One switches is flow the half of the input current, and this one switch is on, the current flow like that, and switches this one on. At T equal to what to say? This one the expression only for the steady state and not transient. Transient will be different. This one will be in a steady state current, like a V in. In transient, if you take a transient current, current is a different thing. Then you can't take a directly as this one. Because the question is given like output current is the constant. That's why I have taken all of the thing in the steady state only. Yes, yes, yes. Uh, in a this you can t equal to 0 current. What will say? Yes, yes, yes. No, this I think you not can't say directly as in a transient system. If in a steady state, you can say this one what is this current and this current. But transient condition, whole expression will be different, and time constant also occurs there. Like what will be the current? Sorry, in inductor resistance will be also inductor and resistance both occur. That's why the RL circuit is there. And the transient condition will be different. All of things. This will condition only for the ideal case. When and question is given, the output current will be constant. And whole of the express this one is the analysis is occurs in ideal condition and steady state. If you take in the practical cases, then you can't say output voltage is constant. Output voltage also vary in practical cases. Because that's why the capacitor we use to take the constant current, constant voltage. And then constant output voltage also vary. Then you can't say this current will be the whole linearly pure linear current. Pure linear current occurs only if the output voltage, input voltage will be constant. If output voltage is some variation occurs, then you can't say inductor current will be purely linear value, linear in nature. That's why. Yes, yes. Yeah, that time it's given only the steady state value. Because of the devices, the pulse current will be more. I think 10 to 15 times of the steady state current. That's why it will not take a transient current. It will take a steady state current. In the steady state current, you can take a maximum current like that. This one IL. If you take a IL current, this one is IL. IL same as the I naught, and whole of this one is the delta IL. Then if you take I maximum, I maximum is I naught plus of delta IL divided by 2. This one is the maximum current. This current, yeah, I max. This one diode. Both of diode. The diode current will be this current. And switches take this current, peak current. Switches rating current should be greater than this current. In this condition, you can say that switches current will be half of the input current, then P output plus 2 into I input current divided by 2 plus ID. ID you can say is as output current of to half of output current. Diode current of output side is a flow like output current will be constant output current. If constant output current, then this current flow through the two diode in the different cycles. That's why you can say as in the average in the diode current is just half of the output current. Yeah. Yeah, I've taken both diode drop at the 0.5, 0.5. That's why I've taken the 1. This one is the 1, 1, this one 2. Yeah. Yes, sir. Switch current. Yes, ID is the diode current. Yeah, 0.5 already taken. Wait. And this one is a 1 voltage taken as switch current, switch voltage. Yes. 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 This is an averages I will take. No? Like this. Power. If you take a power, then some of losses occurs a hold of the switches. Na. Both switches occur, power loss occurs. No? That's why I take both switches losses. The switch current and because of the switch current, every switch current is the same, passes through the both diode, both transistor. There's a losses you can take both. No? You can take only one. Yes. Yes. Because of not in the question is not given much details parameter. That's why you can take as the average of this one. The average of source transistor and the diode average of diode power losses. And ISO switches current will be half of the input current because of the two switches uses, and diode current should be the average of the output current because of two diodes supply to the output current. Yes. In that type of system you use. Yes. Yes. Controllers. No, you can add a capacitor in series combination of the transformer only to deflect this. Yeah. All of things because of the same flux locking phenomena occurs in half bridge, full bridge, push pull. Yeah, capacitor you use for the current control only because of the leakage inductance occurs in the transformer. That's why capacitor is used to control the current only. Yes. Flux value will be reduced when the capacitor is used. The daytime I provide here. This one is both switches on off at that time. Then daytime not a big issue here because of the you provide off time. One switch is on and then off time or total off, and after the second switch is on. If this one is occurs at same time, if Q1 is on, after that Q2 is on, that time you should provide this one, that time you should provide at that time to fully turn off the switches. But here you have enough time to turn off the switches. The switches charge carrier is remove at that time. Yes. D2 ratio should be less than 0.5. Should be less than 0.5. Yes. 45 maximum 0.45. Because of you use the transformer use and DC source you used. Then you should have a condition, some condition to operate the transformer. That would be 0.5. If you increase this one, then the flux will not balance in transformer. Then transformer goes to saturation. Yes. No. This type of thing, I have to use the delta IL only. It means ripple current of a inductor. If you take up too much high of inductor, a ripple will be zero. Yeah, like that, ripple is very minimum. Then your converter is not working properly. Because of this one is DC system and apply inductor. Inductor is not work on the DC system. Constant DC current we can't apply through the inductor. It should have a ripple in the inductor. That's why you can't take too much high of inductor value. That's why you provide a delta IL to 10% to 40% only. If you take a maximum delta IL is to minimum of 10%. Yeah, it should have in your system. Yeah. You can't remove the ripple current because of the inductor. Inductor can't apply a constant current through the inductor. Okay, V in you can return as a V in and I input is equal to P output is equal to plus I in plus I naught by 2. I naught is 30 ampere, 30 by 2 is 15. V in is given, I have calculated V in is 50 volt. 50 I in minus of I in is equal to output power. Output power is given, input power we calculated 720 volt, 20 watts. This one is output voltage and output current plus of 50. Then you can calculate the input current here. 7 of 35 divided by of 49. I think this will be 50 ampere. Next question is given like a refer the question number 2 of same question. What will be the peak inverse voltage rating of the diode if the input to the converter is supplied through the full bridge rectifier capacitor filter connected to 230 volt supply with a 10% of tolerance. Is given an input voltage supply from the full bridge diode rectifier. VS is given at 230 volt, tolerance of 10%, plus minus of 10%. What is the maximum voltage? I think 53 volt. Sorry, I mean into a V maximum voltage V is equal to VM, V is equal to RMS into root 2. Yes, 257.8. Sorry. Yes. Okay, thank you. This is maximum voltage. Maximum voltage आकर है ना, it means VP is the maximum. VP is the maximum voltage of Vs. VP max is equal to Vs maximum minus of 1, because of the 1 voltage occurs on the switches. Switches drop is given. The screen is visual. Now okay, I do it. Please calculate Y1 also to what is the peak inverse voltage of diode. It's okay. Okay, thank you. The VP maximum is a input voltage maximum. This one is a V in. You can take this one maximum. Yes. If you apply capacitor also, then at some time when capacitor is charged, like some duration of time, this one will be like that. This is the output voltage when a capacitor voltage, when full bridge rectifier capacitor filter we used, this was the maximum voltage of VM only. Then VM I will calculate it as a 357.8 volt. Then VM same occurs here at that time. Then VP is this voltage minus of switch voltage. This 1 volt minus of 1 volt. And what will the voltage inverse voltage occurs at the diode? Take as switch 1 is on and switch is on, then this voltage occurs here VP. After that this one is the VS, this one also VS, and this time the D2 will be off. Then what will the voltage of this one? VD. This one voltage is like that. Minus VS is 2 VS. 2 VS minus. Now you can say this one is the voltage also. Diode. If a diode is not given, not taken, then if a diode voltage is taken, then this voltage is also taken. 0.5 volt. Then the 2 VS minus the VT1 is equal to 2 VS minus 0.5 into NS, and VS is equal to VS maximum या VP minus 1 into NS divided by NP. NS divided by NP is given 0.25. Sorry, this one is only minus of this one, like that. Then VD1 is equal to 2 into VS. VS is equal to VS maximum minus of 1 into NS divided by NP minus 0.5. 2 into VS maximum. VS maximum is calculated 357.8 minus of 1. 0.25 is given, NS by NP minus 0.5. Then VD1 is equal to 357.8 minus of 1 into twice 2.25. So only 177.9 or approx 178 volt. Peak inverse voltage of the diode. Okay, a full bridge DC-DC converter is fed from the DC link voltage of 48 volt. As shown in the figure, the ratio of transformer magnetic ratio NS by NP is given 6, and the converter operates at a switching frequency of the 50 kHz with relative ratio 0.5. The peak inverse voltage of secondary side diode D1 and D2. Same thing, if this one is switches on, and VDC appears here. And what will be this voltage? Same NS by NP into VDC. NS by NP is given as a 6 into VDC is the VS, and this voltage same as here. This voltage occurs at diode D2. Then similar to VS, VD2 is equal to 2 of VS, and VS is equal to 2 of VP into NS by NP. VP is same as the VDC because of switches voltage is not the given drop voltage. Then 2 into VP is 48 volt into 6. And calculate this one. 5 plus 76 volt. If you observe the working of this full bridge converter is same as a push pull converter, and switch yes, yeah, minimum you can take a 20% of tolerance also. Yeah, minimum of this one 1.2 into this one video. Yes, yes. Yeah, this one is too much enough. So yeah, this one is a theoretical problem, but in a practical thing is different. You can that's why you take a day, I think 50% or more to the rated value, peak inverse value, because of the some spike occurs when the switches inductor is present in the circuit, LC circuit, dynamical circuit, then spike is also present. And if you design a practical circuit, then it will be take as a 50% more, I think 150% of the peak inverse voltage. But 120% if a proper circuit is there, then you can take 20% more of this, then it will be enough. This same as if you say when S1 S2 is on, then this voltage appears here NP, and that current flow like that, and both are switches off, both are switches up, then same current flow like that. In the push pull converter, same as the push pull converter, this current flow like that to both winding. After that, when say S1 and S2 S4 on, then negative of current flow here, because the VDC is negative. If it is positive negative, then PS is connected here, then this one is positive, this one negative, then current flow, input current flow to the negative of this one IP, reverse wise in this direction, and that time this diode will be conduct, and after the both all the switches off, the same thing occurs. Current flow is I like a push pull converter. If I take S2 S3 on and all of off, after then S1 S4 on, then all off. Inductor current, as when this one is on, current is increases, after that this one increase, this one decrease, like that. So given as a 0.5 turn ratio, then this 0.5 means on and off time will be same. And what will be the flux of this one? Full bridge converter. And switch is on in positive direction, and so then flux will be increased like that to positive to negative something. After the switches is off, all the switches of primary winding voltage will be 0, and that time the current flow like that. Then this one is the positive, this one negative, VS1, VS1, this one is big, the current flow like that, then this one positive, this one VS2, because the turn ratio is the same, then VS1 and VS2 will be same. Then this will apply the KVL here, the secondary side voltage VS is equal to 0 and VA in is equal to also 0. The voltage is constant, so 0, then the flux will be a constant when switch is turn off, all switches. After the S1 S4 is on, then same flux will flow through the negative, from positive to negative, like that. In negative time and all of off, then same flux is maintained in the core of the transformer. Then shape of the flux is like that, trapezoidal. When switch is off, then voltage will be off, then flux will be maintained constant. After the negative voltage appears on the core, then slope will be negative, decreases flux from positive to negative. After that, this one constant. And next switch is off on, the cycle of on. The flux of the in the push pull full bridge converter is like that. The question is so given here. Different the question of flow flux in the transformer pole is this one, trapezoidal in nature. Repeat the question for the secondary side. Secondary of the full bridge converter is modified as shown in the figure below. The peak inverse voltage of the diode. Then auto switch is on, this one switch. Then VDC occurs here. Then what will be this voltage? Vs, and that gets in this NS divided by FNP into VDC. This switch is off. Sorry, this one positive voltage, this one negative voltage, then this one is turned on, forward bias diode, and this condition, this one is negative voltage, this one is a forward bias. And what will be the voltage of Vs here? Negative voltage. Same, this one voltage. Because of this one is connected here, with forward bias, this voltage is just VDC. This one Vs. You can calculate the peak inverse voltage of this one. NS is in NP, same as given 6 into VDC is 48 volt. 288 volt is the peak inverse voltage. Consider practical synchronous buck converter has the duty ratio of D and the equivalent resistance is RL, R1 plus RL. Okay, the output impedance of the converter is of the form of this one. I think small signal losses, you know about the, all of you know about the small signal losses of converter or transfer function of the converter, how to find transfer function of transformer or state space analysis of the transfer converter. This because of this one question is from the state space analysis of the converter. It means when you design a controller for any converter, then you should have a transfer function, have a plant transfer function, like that. If you have a any controller, you know about the reference value. After that, you have a controller. Then you should have a plant transfer function. Then this one is the output voltage. This is the feedback error signal. And controller, what happened? Controller should minimize the error output into input and output. Between the input and output, error minimize the error by the controller. After that, plant this one to maintain the output voltage. If you take as a output voltage of 48 volt, this one is the converter, buck converter or boost converter, like that. And this is also the reference given, this is 48 volt, and controller control the duty ratio of this one. It means you have output voltage and controller, you have a duty ratio of this one. Then you should have a transfer function between output voltage to duty ratio. This is the plant transfer function. To apply this one is the duty ratio. You can change only duty ratio of the converter. None any kind of thing you can change. Once you design this one, the voltage, input voltage, you supply the input voltage. You can't control like always. You can't control always to when you find output voltage is constant output voltage. Main resistance is the load is a constant. And once you design the inductor and capacitor, then you can't change. Switches duty ratio, you only change the duty ratio only of any converter. To change the duty ratio, you can control the output voltage. To control this one, you should have what plant transfer function or converter transfer function you should have. After that, you can control this one. So to find the transfer function of any converter, you should have to in a losses of a small signal. Because of the converter is not a purely linear system, it's some non-linear parameters also occurs in the converter. Because of the, if you take as a constant, so in the ideal cases, as a constant output voltage, constant input voltage, the time the inductor current will be constant. But in practical cases, there will be not output voltage is not constant only, and ripple current occurs. The ripple is not purely linear in those cases. Then you can find a linear, or you can convert in linear by the taking a small amount of thing. Like that, if you have a non-linear system like that, then you can analyze the part-wise transfer function. Like this one, if you take this one as a linear, after that you can take this one as a linear. In that condition, you can take this one as a linear. Then part-wise linear of any non-linear system, you can make a part type linear, stepwise linear. That's why you should analyze any converter as a small signal in losses. A small signal in losses, it means if you have a DC system and output voltage is not constant, if output voltage occurs like that, and by this some point, in practical cases, if you see in practical cases, then the output voltage is not like that, this one constant. It will have some ripple output voltage. Like that. It will you can observe in simulation, NPTEL Live simulation also. Then this one is the DC value. DC value means this one is a constant of DC value, VDC. But some ripple occurs here. Ripple think it means AC signal. If anything ripples occur, then it means the AC signal is included in the DC signal. Then this signal is known as a small signal or small AC signal. Then you can analyze this signal, a small signal, and then you can minimize the ripple of this one. That's why it's also said as a small signal in losses of converter. If you observe this, if you read in the book also, you can take a help from book and then you can find the analyze the small signal losses of the converter, buck converter, boost converter, or any converter to design a controller. You can design a controller only when if you know about the transfer function of a plant or transfer function of the converter with respect to output voltage to duty ratio. In this case, like that. If you have this one as a transfer function, then you can take as a make a controller like a PID controller or another controller, a compensator also you can design from this one to find the gain margin and phase margin, or to take a limitation of the gain margin and phase margin. So many things occurs, but to control any system, you should have a transfer function. After that, you can apply the controller to the system. That's why this one is the only, this one is the from the controller only. Okay, I have take a second question, is a normal question. After that I will go over there. A simple buck converter. Buck converter, this one also buck converter, but resistance is there. That's why it will take us some complication. So first I will explain this one. The ideal buck converter, so assume as the IL, the same as the IL. It will be same when then IL variation of IL is equal to variation of IC. This one is the perturbation of variation, you can say. Because of this one IL, if you take a average of IL current is same as the, you know about the same as the output current. But ripple in inductor current is same as the ripple of the capacitor current. That is represent this one. A ripple of inductor current same as the ripple of a capacitor current. Same ripple occurs, and average of the inductor current is same as the average of the output current. That's why IL is written as IL is same as the IC. The inductor ripple current is the same as the capacitor current. To analyze the system, first one find the Q on time. What is the inductor voltage? We have only two energy storing devices, L and C. Then you have, if you have a two energy storing element, then you have a two second order the system. You can find only second order system. If one energy storing system in your plant, then you find only a first order, one order system. If three storing element is there, then third order expression you can find. The energy storing element define the order of the system. Then you have a two thing, then you can take only two order system. A variation of this one you can take because of the V input and output voltage. Resistance is not a storing device, is not a dynamic device, only the static thing. Then you can observe this one. Only in the inductor cases, you observation is the inductor current. In capacitor cases, you observe the VC, capacitor voltage. Look, when switch is on, VL is equal to V in minus of V naught. Then VL you can written as LDI by dt. And IC current you can written as IL minus of I naught. IC is a same dVc by dt. This one and Q is 1 or switch is on. Then switch is off, Q is equal to 0. Then inductor voltage is 0. This one switch is on. This one appears as a minus of V naught. L DIL by dt. Then in capacitor current is the same expression, IL minus I naught. IL minus of I naught. IC you can written as dVc by dt. Take this one is the third equation, this one is the fourth equation. Then combine this one. Next step is the combined of inductor current voltage, and second thing is combined of capacitor voltage, capacitor current. If you combine of inductor voltage, then you find L di by dt. Total di by dt is equal to this one is duty is on, dV in minus of V output plus when switch is off, 1 minus d into minus of V naught. This is the state of this one, inductor current. Di by dt, you know about dx by dt. X dot in control system, you read this one is the state of this one equation. A state occurs when the dynamic system is occurring in the same law. Then dv in written as dv in minus of dv naught. This one minus of v naught plus of dv naught. Dv naught is cancelled out. dv in minus of v naught. L di by dt is equal to dv in minus of v naught. Equation number 5. Same can say dvc by dt into the capacitor current, d into il minus of I naught plus of 1 minus d il minus of I naught. Then cdvc by dt is equal to, if you take this one, then only 5 il minus of I naught. D into il minus I naught, 1 into il minus I naught into minus d of il minus I naught here. Then d into il minus I naught cancel out, il minus of I naught only present. This one is your equation when averages equation of inductor voltage and capacitor current. This one switch is on and off if you combine this one. Then we have an average state of this one. After that you do the small analysis of the this is two equations. If you take this, if you realize this one, then first to find the IL current. IL current, you have IL ripple plus a average current. Then VC voltage. VC is the voltage same as the V output voltage. Capacitor voltage is same as the output voltage. Then output voltage ripple, capacitor voltage ripple plus a average voltage. This is the perturbation of this the signal or the parameter. Duty ratio will change as D cap plus capital D. Replace this one. If input voltage variation occurs, then we take a variation of input voltage plus of average of input voltage. Sorry, average of input voltage. You have inductor current variation in the input average inductor current, and variation in the capacitor voltage and average capacitor voltage. Average capacitor voltage is same as the average of output voltage because the capacitor connected directly to the pillar of the output. Duty ratio variation and constant duty ratio, average duty ratio. V in is the input voltage variation and input current, input voltage, constant input voltage. Same thing replaced to here for the inductor voltage and inductor capacitor current. L di by dt, IL replaced by the IL cap plus IL. From equation number 5. IL cap plus IL divided by dt is equal to dv in d plus d cap, v in is equal to v in cap plus v in minus of v naught. V naught is equal to vc cap plus of v output. L DIL cap by dt dv in cap, we multiply this one plus dv in, after that d cap into v in cap plus d cap into v in minus of vc minus of v naught. dv in cap plus d cap v in minus of v c cap. Here d cap in v is v in cap. It means small changes in v due to ratio small in the input voltage. This variation is very small is respect to other. That's why you can take as a neglect of this term. You can neglect of this term because of this one is the very small. Due to ratio changes the very small also, and v in variation is very less. That's why you can neglect this term and take the dv in plus dv cap by v in only. After that you find plus of dv in minus of v naught. You can take written as L DIL dt is equal to dv in minus of v naught. Then L DIL dt is equal to dv in upon minus of dv naught. If you can written this one is L DIL by dt, then this will be cancel out this term, then you will find only the variation term. Delta IL by dt is equal to d v in cap plus d cap v in minus of vc cap. Equation number 7. Same thing apply for the equation number 6. C dvc is equal to IL minus of I naught. I naught you can written I naught is equal to V naught by R, and that's why I written here V naught by R. dvc written as dvc cap divided by dt plus c d v naught at dvc average. So IL cap plus of IL minus of VC cap by R minus of V naught by R. Same thing, IL minus of V naught by R, you can declare you can cancel out this term, then you find as a dvc cap divided by f dt is equal to IL cap minus VC cap divided by R. Equation number 8. From equation number 7, equation number 8, you can retain as delta IL divided by dt cap is equal to d by L into V in plus dv in sorry delta VC cap by dt is equal to IL cap divided by C minus of VC cap divided by RC. 9. Sorry. This one you can return as IL dot VC dot, and you can retain the matrix like IL cap dot, leave it directly written as IL dot IL by dt and d VC by dt. IL cap VC cap. Sorry. IL cap in there in this question number 9, LDI by dt, that it means this one is 0. VC is here minus IL by L minus 1 by L. Equation number 2, VC is IL is given, then I1 by C here, IL will take common, and VC is minus 1 by RC. D cap here, that means V in by L. Here D cap is not there, then 0. V in only 1% here, D by L. This one matrix of A, this one B matrix, and C matrix again the output voltage. Then output voltage you can return as V output is equal to VC, same as the output voltage. Then VC you can return as IL cap VC cap, then return 0 1. To multiply this one matrix, then you find only VC. V naught is equal to VC. Then this is the output voltage, then this matrix is C. ABC matrix, this one is the input matrix. Then you can take anything. This thing you can observe this one X dot. In the control system you reading in control system is X dot is equal to AX plus of BU and Y is equal to CU. Sorry, CX. Same thing occurs here. X dot is equal to, this one you can take as X dot delta L, because of the dot is equal to X dot is equal to d by of dt with respect to X. This is X dot. Then you can take delta IL. This one is the state. This one is represent the state, and this one is a differentiation of a state, next state. And this one is represent the input. This one is the output. This one is the state of thing. In control system, you know the transfer function C S I minus A of inverse into B. You can find a transfer function of the system. But here to find the transfer function, V output is taken, C is the V output and B is the input matrix. Then you can find V output divided by D cap only. This one is transfer function you find. To find this one, then take a V inputs by reason should be 0 because of the single input, single output system here. That's why you to represent the transfer function for the single input, single output system, then variation input taken should be 0. You observe the, it means you take as the input voltage should be constant. In that condition, you can design a controller to find the transfer function from this one Si minus A of inverse into B. So if you apply here si minus A inverse into this, you can find transfer function. This is state space analysis of the converter, a buck converter. Same thing you can do for the boost converter and buck boost converter. If any converter to design if you want to design a controller, of any converter, then you should have to find the transfer function of the converter. To find the transfer function, then find the state space analysis. After that, you find the transfer function by this one. Yes. Same thing, same black diagram. Draw here. This one is transfer function, and the controller you should design. You design a controller. Yeah, you design a compensator. The first of find it plant. Plant is the transfer function. Then you find the input. Or you can say this one is the. You find V output divided by D cap. No, it means that this one D, this one V output. Then you find D, this one transfer function. You can also say that this one is the open loop transfer function. It is not a closed loop because you find a D here, input given D here, and output find here. You have a plot this one. Then you find a V output voltage. This one is D. Duty ratio you do to the converter. Only you can give the duty ratio. Then you find input as the duty ratio. Then you have to design a controller by taking the closed loop system. Taking the closed loop system, then you find a controller. After that, like if you take this one controller, if you this one K, this one GS, connect. You can write as the transfer function. Open transfer function is GS. Then our controller is like a GC. Yes. Then you find our closed loop transfer function. GS divided by 1 plus GS into HS. So GS into GCS divided by GS into GCS. HS is 1, then this one is 1. HS is feedback system. Feedback gain. This one X is the state of the plant, state of the system. You have a two state because you have a two dynamical component, energy storing element L and C. The inductor storing is the current form and voltage storing the charge or voltage form. That's why you have a two state, IL there and BC. This one is the state. X is the represents the state, and next dot is representing the differentiation of state. This one. This one is not a single liquid. This one is the matrix. X is on the matrix, and X dot will be maximum. U is also matrix form. If you have two energy element, then you have a 2 cross 2 matrix. If you have a 3 energy element, the energy storing element, then this matrix will be 3 cross 3. Yeah, this one is the state of the converter, state of the system. If you design a controller in that time, this thing here, you sense continuously na output voltage and input inductor current. You sense continuously na. But if you want to generate in once time, because of the L and C will be constant. Look here. Here, what is the variation value? Variable value what is that? You have a designer, you have already designed an inductor, capacitor and resistor is the same. You can't change this one. V in also will take as a constant. Then only you have a duty ratio only. Once you design this one, then you can't change the inductor value and capacitor value. You have only the duty ratio to change this one. This changes occurs when the you have this changes occurs from the controller only. Controller will change the duty ratio. Then you sense the output voltage like this one. So sense the here output voltage and take a feedback given a difference value. After that you should take a controller. This one. Yes. Yeah, in that time it's the different kind of type of controller. If you take as a simple as a controller design, this one only for the find the transfer function of the plant only. After that you want to take a design a controller. The controller design once is with respect to the plant only. This one controller has two types of design. Yeah, tracking controller or a simple controller used. There is like a PID controller, yeah, compensator. In PID controller, what is the this one PID controller is again like a Kp plus Ki by S plus S of Kd. Then you once fix this one gain of PID controller Kp, Ki and Kd. If you design, if you have a plant and you have fixed this one controller, that you cannot change this one. Controller once designed with respect to the plant transfer function. You have a plant transfer function. To see the plant transfer function, you design a PID controller. Once you design a PID controller, then you did not need to change the Ki. You can't change the Kp, Ki, Kd value in the running condition. This one is the constant thing. But if you want to change this one in the running condition, then this one says like a robust control. In that condition, you should track the output voltage, input voltage, output voltage and inductor current. You sense both to give the feedback, inner loop and outer loop, a two loop is there. After that, you design a controller to control this one, whole of thing. And that type of controller you should need the both. But here for a normal controller, PID controller or the compensator, simply you design to take in the account of the plant transfer function only. Because I have the yeah. Because of in power electronic system, any converter, you can change only duty ratio of the switches. You can't change another thing in the controller, the converter, because of the resistance of load is not in your hand. And once you design a converter or capacitor value, inductor value fixed. Switches you fix this one. You can't change the switches in running condition. Input voltage not in your hand. Once you apply input voltage, input source, then leave it. It will control. We have only to control the duty ratio of the switches. That's why I take a VI by VT. This one. Yeah. So then at that time you should find IL by D cap. In this thing you control the input inductor current. And you want to both control, it's like a constant voltage and constant current. You know, to charge the battery, you should have a constant voltage and constant current charging controller. Like that you want to make. Then to take this loop, this transfer function in the inner loop. After that V output by D cap, take this one as an output loop. At that time you have a two controller. We should design a two controller. Inner, this one inner loop, this one outer loop. Inner loop time constant should be less than the outer loop, because of this one take at much low time after the output controller. You can take account of this. Okay, I am stopping here. Thanks to all.